Hi, all. Today we're going to continue on with topic 10, rate law expressions, except now what we're going to try to do is to try to figure out what the order of the reaction is using raw data. So we're going to see how we can actually figure out what those exponent values were in the rate law expressions that we were working on the previous lesson. So if we look at sample problem 4, it says under acidic conditions, hydrogen peroxide, H2O2, oxidizes iodide ions, I- to triiodide ions, I3-. The balanced equation is shown here. A chemist runs a series of reactions using a method of initial rates. She varies the initial concentrations of the three reactants as shown in the table below. Using this data, determine the reaction orders with respect to H2O2, I- and H+, and state the rate law equation for the reaction. Okay, so for this, what we're trying to do is to figure out the rate law expression. So based on this equation here, we can write out a rate law expression. So if you can take out a moment to do that. Now, that rate law expression should look like R is equal to K times the concentration of H2O2 raised to the power of M times the concentration of I- raised to the power of N and the concentration of H+ raised to the power of P. This is just a generic rate law expression. We arbitrarily chose the exponents M, N, and P to indicate the orders for H2O2, I- and H+ respectively. Now, to try to figure out these order of reactions, we need to analyze the data. Okay, and what we're going to try to do is to find runs where the concentration of one of the specified reactants changes and the rest do not. So if we look at runs 1 and 2, okay, so in this table we can see that we have 4 different experiments that are done where we have different concentrations of hydrogen, H2O2, I- and H+. Okay, and if we look at runs 1 and 2, we can see that the concentration of H2O2 changes from 0.1 to 0.2 moles per liter. But in the other reactants, the concentration of I- does not change, it stays the same. And if we look at the concentration of H+ here, it remains the same. So the change in concentration here is going to be responsible for the change in rate that we observe. So what we can see here is that if we double the concentration of H2O2, the rate of this reaction is going to double. So here we have 1.5 times 10 to the negative 5, and in run 2 we have 3.0 times 10 to the negative 5. And if we divide those two numbers, we're going to get 2. So if we go down over here, we can see that for H2O2, if we double the concentration of H2O2, the rate will double. So we need to try to find out what the order of the reaction is. So in this case, because if we just double the concentration, the rate also doubles, the order must be 1. So M must equal 1 for H2O2. Now we're going to do the exact same thing for the rest of the reactants. So we're going to go and look for 2 runs where the concentration of I- changes, but the concentration of H2O2 and H+ remain the same. So if we look here, if we look at runs 1 and 3, we can see that in run 1, the concentration of I- is 0.1, and in the run 3, the concentration is 0.2. Now, if we look at H2O2, in these runs 1 and 3, the concentration remains the same. We have 0.1 moles per liter in both of those runs. And if we look at H+, the concentration remained at 0.0003 moles per liter. So this doubling in rate will be responsible for whatever rate change we see. So if we look at the rate change between runs 1 and 3, we can see that in run 1 we have 1.5 times 10 to the negative 5. And in run 3, it is 3.0 times 10 to the negative 5. So similar to the last scenario, the rate also doubles. So we can say for I-, 2 to the power of n is equal to 2. If we double the concentration, the rate will double. Therefore, the order of the reaction with respect to I- must be 1. Now we're going to go and do the exact same thing for H+. So if we're looking at here, if we're looking at runs, let's say if we wanted to go through and look at runs 3 and 4, we could not choose those as the ones that we would choose to try to see this rate change. Because if we look here, you can see that the concentration of H+ here doubles. The concentration of H2O2 remains the same, but the concentration of I- changes. So those would not be an okay set of runs to look at to find this rate change, because the rate change that we're going to see if we chose those two runs will be because of I- and H+, not just H+. So we need to keep in mind whenever we're looking at runs, we're looking to see where the concentration of that specific reactant changes, but the rest of them remain the same. And we see that in under runs 1 and 4. So we can see that the concentration here changes from 0.0003 to 0.0006, and the concentration of H2O2 remains the same at 0.1, and the concentration of I- remains the same at 0.1. So here we have the concentration doubles, and now if we look at the rate stays the same. So we have 1.5 times 10 to the negative 5 for both. So the change would be 1. So now we can say for H+, 2 to the P is equal to 1. So if we double the concentration of H+, the rate does not change. So the order, or P, must be 0 for H+. So now we can go through and rewrite this rate law expression to write the orders that we identified. So the rate law expression for this reaction would be R is equal to K times the concentration of H2O2 to the power of 1, I- to the power of 1, and H+ to the power of 0. We can also rewrite this to completely omit H+ since its value is 0, and write it as R is equal to K concentration of H2O2 to the 1 and I- to the 1. Now, whenever we're trying to solve for the rate law expression, we also must solve for the value for the rate constant. So to do that, all we need to do is to plug in the values for one of the experiments. So we can see here, to solve for the rate constant, plug in the values for one run into your rate law expression. So we had this as our rate law expression here, and all I did was I chose the values for run 1, where the rate was 1.5 times 10 to the negative 5. It's equal to K times 0.1 to the power of 1 times 0.1 to the power of 2 for our I-. As you can see here, we plugged in these values. Okay? And if we isolate for K, we get a value of 0.0015. Now, the overall order of this reaction is 2, so the units for K are going to be liters per mole dot seconds. Okay. Now, when we're plugging in our values here for K, don't worry about including your units. It's not necessary, but it is necessary that you are including the units for the value for K. Okay. So I'm just going to go back. So this is going to be a question that you're guaranteed to see on any type of assessment. And it's something that you're going to be seeing next year. So we're going to try to work through 2 more examples to give you a little bit more practice, but you're going to see that the logic and the workflow is going to be the same. Now, if we look through here, I have another description of our answer to this problem. It gives you a little bit more of a breakdown and written explanation for it. So you can read through that on your own time, and it does go through to try to explain it for you. Okay. So what I'd like to do is we'll start going through sample problem 5. I'd recommend that if you can maybe pause the video and try it on your own first, and then go through and listen to the explanation. Okay. So in this question, it says, when aqueous bromine and bisulfite ions react to produce bromine, the overall reaction equation is written as here. And here there were a series of experiments that were done where the initial concentrations of the reactants were changed and the rate was measured. So in here, we have to do the exact same thing. Okay, so we're going to go through and write out a generic rate law expression. So that's going to be R is equal to K times BrO3 minus, the concentration of BrO3 minus to the power of M, and the concentration of HSO3 minus to the power of N. And it's always going to be R is equal to K times the initial concentration of the reactants raised to some kind of power. Okay. Now, we're going to go through and start with the first reactant. So I chose BrO3 minus, and we need to figure out what the order of the reaction is with respect to it. So we're trying to find two runs where the concentration of bromate changes, but the other reactant remains the same. So if we look at runs 1 and 2, we can see that in the first run, the concentration is 4, and then the second, it's 2. For HSO3, it remains 6 under each scenario. Now, what I'm doing is I'm just comparing runs dividing 4 by 2 instead of doing it the other way around. It just makes it a little bit easier. I like dealing with whole numbers instead of decimals. So in here, as we're going from run 2 to run 1, the concentration doubles. And if we look at the rate here, the rate goes from 0.8 to 1.60. So it also doubles. So we can go and say 2 to the m is equal to 2. So if we double the concentration of bromate, the rate also doubles. So the order with respect to BrO3 minus must be 1. Okay. Now, if we're looking for HSO3, if we're looking at runs 2 and 3, we can see that in run 2, the concentration is 6, and in run 3, it's 3. For bromate, it remains the same. So we can look at these two runs. So we can see that the concentration doubles between run 2 and 3. But now if we look at the rate of the reaction, it goes from 0.2 to 0.8. So the rate actually quadruples, so it increases by 4. So now we can say 2 to the n is equal to 4, therefore n must equal 2. So this is second order with respect to HSO3 minus. So we can rewrite this expression to say R is equal to K, concentration of BrO3 minus to the 1, and HSO3 minus to the 2. Okay, and that's our rate law expression. Now, we still need to solve for our value for our rate constant, and to do that, we're just going to plug in our values for one of the runs. And I chose run 1, so I plugged in 1.60 for the rate, 4.0 for the initial concentration of bromate. It's raised to the power of 1 because the order is 1, and put in a concentration of 6 for HSO3 to the order of 2. From there, we solved for the values for K, and we should get something on the order of 0.0111 liters squared per millimole second. Sorry for the error here. So it's liters squared over moles squared second because the total order of the reaction is 3 because it's 1 plus 2. So it's going to be 1 less than that. Okay, last problem. So in here, mixing an acidic solution containing iodate ions with another solution containing I- ions begins a reaction that proceeds in several steps to finally produce molecular iodine. So the data below shows the data below were obtained for the rate of production of iodine. And we're asked to solve for what is the rate of the rate equation for this, so the rate law expression. And in B, we're asked to solve for the rate at a specific set of concentrations. So we're going to go through and write out our rate law expression. So we have R is equal to K, concentration of IO3 minus to the M, I minus to the N, and H plus to the P. And we're going to go through to try to find out what M, N, and P are. So we're trying to find, for IO3, we're trying to find a run where it changes, but the concentration of the others remain the same. So we can see for runs 1 and 2, the concentration doubles, I minus stays the same. And looking at here, our rate also changes. So going through the concentration doubles, here if we look at these values, we have 5.0 times 10 to the negative 4 and 1.0 times 10 to the negative 3. And if we divide those numbers, we're going to find that the rate doubles. So we can say 2 to the m is equal to 2, so m must equal 1. Now, for I minus, if we look at runs 1 and 3, the concentration triples, no change in IO3 minus and H plus. Here, the rate also triples, so we can say 3 to the n is equal to 3, therefore n is equal to 1. For H plus, we're looking at runs 3 and 4. Here, the concentration doubles, no change in IO3 or I minus. Here the rate quadruples, so it goes up by 4. So we can say 2 to the p is equal to 4, therefore p must equal 2. So we can rewrite this rate law expression to say r is equal to k, concentration of iO3 to the 1, I minus to the 1, and h plus to the 2. And from there, we can solve for our rate constant by just plugging in one of the runs. I just chose the first one, and we get a value for K of 5 liters cubed per millimoles cubed seconds. Total order is 4 because it's 1 plus 1 plus 2. So our units for K are liters 3 over millimoles 3 seconds. The second part of the question asked us to solve for the rate at these specified concentrations. So all we need to do is take our rate law expression that we had and plug in the specified concentrations. If we do that, we'll get a rate of 4.0 times 10 to the negative 3 millimoles per liter second. That concludes our rate law lesson. Your homework's going to be trying to analyze similar data to try to write out the rate law expression and come up with your value for K. So by now, we should be able to try to determine the rate of a reaction using rate laws and determine the order of a reaction with respect to a reactant and or a product, as well as the total order of reaction and explain its significance on the rate.